Hello again. Yes, we can start our last section of today's virtual congress series. Just now, we are going to watch one of the pre-recording presentation, BIOMATSEN presentation. Professor Snezana Ilic-Stojanovic from Serbia. Professor, do you hear me?
Yes, hello.
Hello, welcome.
Hello, I hope you enjoyed your coffee break. My name is Snezana. I come from Serbia, from University of Niš, Faculty of Technology. I want to present results from our research performed in collaboration with my younger colleague, Dr. Aleksandar Zdravkovic, from Academy of Professional Studies, South Serbia, Department of Technology and Art Studies, and our mentor, Ljubiša Nikolić, from Faculty of Technology in Leskovac. Let's hear my presentation.
Okay, if you are ready, I am going to start your presentation and we are starting our record.
Thank you.
Dear colleagues, my name is Snezana Ilic-Stojanovic, and I want to present results of our research on the synthesis and characterization of dual stimuli-sensitive copolymer hydrogels performed in collaboration with my younger colleague Aleksandar Zdravkovic and our mentor Ljubiša Nikolić from Faculty of Technology in Leskovac. Firstly, let's remember the basic term of our investigation. Hydrogels are a three-dimensional polymer network consisting of at least one hydrophilic monomer linked with chemical or physical cross-linking. They can absorb and retain a large volume of water without dissolution. There are different ways of hydrogel classifications. Based on the swelling behavior as a response to variation in the external medium, hydrogels are classified as conventional hydrogels, which are not significantly sensitive to changes in the environment, and stimuli-sensitive hydrogels, smart or intelligent, which exhibit significant change of properties due to small changes in the external environmental conditions, such as pH value, ionic strength, temperature, light, wavelength, magnetic or electric field, ultrasound, or a combination thereof. The pH-sensitive hydrogels contain the ionizable functional groups that either accept or release protons in response to environmental pH changes. Thermosensitive hydrogels are characterized by volume phase transition temperature, while linear polymers are characterized by a critical solution temperature. Negative thermosensitive hydrogels exhibit swelling to shrinking transition with increasing temperature. Positive thermosensitive hydrogels show opposite behavior, exhibiting shrinking to swelling transition with increasing temperature. Dual stimuli-sensitive hydrogel, especially pH and thermosensitive, are the most studied class of smart hydrogels. And what are goals of this work? Synthesis of thermo and pH sensitive hydrogels based on monomers an isopropyl acrylamide with acrylic acid or methacrylic acid. Structural characterization of a synthesized poly-N isopropyl acrylamide co-acrylic acid and poly-N isopropyl acrylamide co-methacrylic acid hydrogels by infrared spectroscopy, scanning electron microscopy, and X-ray diffraction methods. Thermal characterization of synthesized hydrogels by differential scanning calorimetry method. Analysis of residual reactants content after polymerization by high-pressure liquid chromatography method. Swelling behavior analysis of obtained hydrogels depending on the content of comonomers, acrylic or methacrylic acid, and the crosslinker, the lyophilization process, as well as temperature and pH sensitivity. Swelling kinetic analysis before and after lyophilization process, and the end, modeling of swelling process for obtained hydrogels by experimental design. In following slides, we can see all reagents used in this investigation as well as method for characterization. Some information about synthesis process. Poly-N isopropyl acrylamide co-acrylic acid and poly-N isopropyl acrylamide co-methacrylic acid hydrogels were synthesized by radical polymerization of N-isopropyl acrylamide as monomer with 5 and 10 molar % of acrylic acid or methacrylic acid as comonomers in acetone as solvent, using the initiator 2,2'-azobis 2-methylpropionitrile and varied concentration of crosslinker 1, 1.5, 2, and 3 molar % of ethylene glycol dimethacrylate under the temperature regime. Obtained hydrogels were extracted with methanol to remove all non-reacted water-insoluble compounds, monomers, oligomers, and impurities. Swollen hydrogels were dried to the constant mass. And now results and discussion. Possible structures of monomers and crosslinker are shown in this picture. An isopropyl acrylamide and hydrogels are shown in this slide. The potential formation of intramolecular hydrogen bond is indicated. And now characterization of synthesized hydrogels. Labeling of the hydrogels samples. In example, 9% of comonomer acrylic acid or methacrylic acid, and the third number indicates molar % of the crosslink. In the next two slides, ethylene like crosslinker, the following bands from characteristic functional groups are marked. Valence vibration from carbon-carbon double bonds in all spectra of reactants are highlighted, and at example 1634 and 1636 reciprocal centimeters. FTR spectra of zero gel samples, polyanisopropyl acrylamide co-acrylic acid with 5 and 10 molar % of acrylic acid have structures different from reactants. The presence of new bands, which are absent in the spectra of monomers and cross-linker, and absence of absorption band from 1620 to 1640 reciprocal centimeter, which originate from the carbon-carbon double bond, confirm successful polymerization. This bond is broken down in copolymerization reactions. FTR spectrum of methacrylic acid is on the top, and FTR spectra of polyanisopropyl acrylamide co-methacrylic acid with 5 and 10 molar % of methacrylic acid co-monomer have structures different from the reactants, with new bands which are absent in the spectra of reactants, and absence of absorption bands from valence vibrations of carbon-carbon double bond, confirm successful polymerization process. X-ray diffraction analysis. Diffractograms of obtained copolymers with 5 and 10 molar % of acrylic acid or methacrylic acid compared with homopolymer polyanisopropyl acrylamide are presented in the next 2 slides. Firstly, polyanisopropyl acrylamide with coacrylic acid. Diffractograms of all samples show similarity, no clearly defined reflections, and indicate semi-crystalline structure. All diffractograms contain 2 wide unstructured peaks. The first peak appears at diffraction angle around 8 degrees. The fundamental wider peak appears at about 20 degrees. Similar diffractograms are for polyanisopropyl acrylamide co-methacrylic acid hydrogels, and diffraction angle values of both zero gels are noted in presented table. The morphology of swollen and lyophilized hydrogels was analyzed using scanning electron microscope. Morphological disorganization and the presence of large pore are observed in the micrographs of poly and isopropyl acrylamide co-acrylic acid with 5 and 10 molar % of acrylic acid. The three-dimensional hydrogel network provides a large free space between cross-linked chains in swollen state. All micrographs show characteristic porous surface and microchannels which facilitate water absorption. Similar morphology can be seen in the micrographs of swollen and lyophilized copolymers with 5 and 10 molar % of methacrylic acid. Copolymers of polyisopropiol acrylamide coacrylic acid and polyisopropiol acrylamide metacrylic acid are macroporous with an average pore size up to 100 and 120 in thermograms of poly and isopropyl acrylamide, acrylic acid and co-metacrylic acid. Analysis of DSC results confirms that synthesized copolymers are semi-crystalline because they melt when heated in wide region. Analysis of residual reactants is presented in next slides. We can see the chromatograms of methanol extracts after polymerization with their ultraviolet spectra of all reactants and isopropyl acrylamide, acrylic acid, and cross-linker. In the next slide, also HPLC chromatograms of methanol extracts after polymerization with ultraviolet spectra of all reactants and isopropyl acrylamide, metacrylic acid, and cross-linker, and quantities of residual reactants relative to the total zero gel mass in a milligram per gram and relation to initial mass in the reaction mixture in mass percent are noted in following tables. Firstly, for hydrogels with acrylic acid as comonomer, and secondly, for hydrogels with metacrylic acid as comonomers. The calculated content of residual reactants is negligible within tolerance limits, and their conversion in the polymerization process is almost complete. The residual monomer content up to 0.5 and even up to 1% or more is often found in polymers produced on the industrial scale. And now, swelling behavior of poly and isopropyl acrylamide coacrylic acid and poly and isopropyl acrylamide co-metacrylic acid hydrogels was studied in the aspect of their pH and thermosensitivity. Results of equilibrium swelling for poly and isopropyl acrylamide co-acrylic acid hydrogels with 5 and 10 molar % of acrylic acid and 25 centigrades and different pH values are presented in the next 3 slides. We can see swelling ratio depends on the time and comonomer acrylic acid content, 5 and 10%. 1 gram of sample with 5 or 10 molar % of acrylic acid can absorb approximately 8 to 10 grams of fluid at maximum at strong acidic fluid at pH 2.2. Unexpectedly, 1 gram of samples can absorb approximately 229 to 260 grams of fluid at maximum at pH 6.8. Also, swelling degree of hydrogels is significantly higher in the alkaline fluid at pH value 9.1. 1 gram of sample can absorb approximately 293 to 372 grams of fluid at maximum. Polyanisopropyl acrylic acid hydrogels are pH sensitive. It can be noticed that equilibrium swelling ratio depends on time, content of comonomer acrylic acid, and pH value. Results of equilibrium swelling of polyanisopropyl acrylamide co-metacrylic acid hydrogels with 5 and 10 molar% of metacrylic acid and 25 centigrade and different pH values are presented in the next 3 slides. We can see that 1 gram of sample with 5 or 10 molar% of metacrylic acid can absorb approximately 6 to 16 grams of strong acidic fluid at maximum at pH 2.2. As expected, 1 gram of sample can absorb approximately 90 to 103 grams of fluid at maximum at pH 6.8. Hydrogels swell significantly better in the alkaline fluid and pH 9.1. 1 gram of sample can absorb approximately 170 and 212 grams of fluid at maximum. It can be noticed that equilibrium swelling ratio depends on time, comonomer metacrylic acid content, and pH value. Copolymer hydrogels with metacrylic acid as comonomer are also pH sensitive. The additional methyl group in the structure of the anionic comonomer metacrylic acid contribute to the higher hydrophobicity of the copolymers with metacrylic acid as comonomer, and to the reduction of swelling capacity compared to the copolymer with copolymer polyanisopropyl acrylamide co-acrylic acid. And now, thermosensitivity testing of synthesized hydrogels showed the volume phase transition from 30 to 45 centigrade as a result of breakage of bonds between the polymer chains and water, which cause contraction of the hydrogels and water release. Reversibility of swelling of obtained hydrogels followed the trend of decreasing swelling during the process of heating and cooling. This trend of fluid absorption capacity decreasing continue in the third cycle from about 3 to 8%. Analysis of hydrogel swelling kinetics before and after lyophilization. In order to study mechanism of fluid transport within the hydrogels, a logarithmic form of Fick equation was applied and diffusion coefficient D was determined. Dependencies of the swelling degree on the time hydrogels, polyene isopropyl acrylamide coacrylic acid with 5 and 10 molar percent of acrylic acid before and after lyophilization in fluid of pH 6 at 25 centigrade are percentage swelling degree of lyophilized hydrogels on the first 4 hours is more rapid than in non-lyophilized samples. Kinetic parameters of these hydrogel swelling before and after lyophilization in fluid with pH 6 were calculated. Diffusion coefficient D confirms that lyophilized hydrogels swelled more rapidly than non-lyophilized hydrogels. Similar behavior of the swelling degree on the time for polyene isopropyl acrylamide co-metacrylic acid with 5 and 10 molar percent of metacrylic acid and before and after lyophilization are presented. The cross-linking degree also influenced the swelling process and with increase the cross-linker amount, the swelling degree of hydrogels before and after lyophilization has decreased. Lyophilized hydrogels in swollen state absorb the fluid more rapidly because the greater pore size enable faster penetration of fluid molecules within the polymer network. Values of diffusion coefficient D of non-lyophilized hydrogels were smaller than lyophilized samples, and more slowly swelling was confirmed. The result of swelling behavior shown that obtained copolymers can be classified as superabsorbent polymers. Modeling of swelling process for hydrogels by experimental design for the evaluation of pH, temperature, and cross-linker content influences on synthesized hydrogels swelling. A full 3-level factorial design has been used. Selection and evaluation of model adequacy and statistically significant factors in the model have been performed by ANOVA test. Factors and interactions whose p-values were lower than 0.05 have been considered to be statistically significant members. Matrix of the full factorial design with experimental values of the responses are presented in this table for polyene isopropyl acrylamide co-acrylic acid hydrogel swelling. The results of analysis of variance quadratic model for equilibrium swelling of these hydrogels are presented. Final equations of the factorial model for equilibrium swelling of polyene isopropyl acrylamide co-acrylic acid hydrogels as a function of temperature, cross-linker, and pH in the form of coded factors are given in by presented equations. A quadratic model has been developed to predict the swelling process for polyene isopropyl acrylamide hydrogels in various pH values, temperatures, and cross-linker contents. two-factor interaction model in the most optimal model of full three-level experimental design for representing the equilibrium swelling degree of poly and isopropyl acrylamide cometacrylic acid hydrogels as function of investigated parameters, temperature, and pH value. And then conclusions. Copolymers, poly and isopropyl acrylamide coacrylic acid and poly and isopropyl acrylamide cometacrylic acid are obtained by the free radical polymerization mechanism. FTR and HPLC analysis confirms successful polymerization process. X-ray diffraction and scanning electron microscopy analysis indicate a semi-crystalline structure of synthesized hydrogels. DSC result show the melting transition of both hydrogels. Thermo and pH sensitivity of obtained hydrogels were observed. All synthesized hydrogels exhibit negative thermosensitivity. Lyophilized samples swell more rapidly than non-lyophilized samples of the same hydrogels. Synthesized both hydrogels can be characterized as super absorbent materials. Modeling of swelling process for obtained hydrogels was completed using a full three-level factorial design, and obtained result and their importance present possibility to apply these hydrogels as promising materials potentially suitable as adsorbents for pollutants or as carriers for active substances. And then, thank you for your listening.
Yes, thank you, Professor. This very interesting and very nice presentation.
Thank you. If there are any questions, I'm ready to answer now.
Yes, I want to warn to all our participants. Do you have any question to ask our professor? Please write, if you want, you can write your questions to chat part, or if you want to ask with yourself, please write the chat part. We can open your voice and you can ask your questions. We can wait a few minutes. I think there is no question for now.
Yes, everything is clear now. But if you have any questions, send me on my mail. I want to express many thanks to the Serbian Ministry of Education, Science and Technological Development for financial support. Thank you very much for your invitation and excellent organization of a virtual BIOMATSEN conference. And thank you for your attention.
Thank you, Professor.